What is this? No, I'm just kidding around with you. Of course you got to do these problems on your own. But we're in a good mood here. This is the last unit. We've only got one final strategy here to look at, and it's indirect proof. Now, indirect proof can be used in two different ways, really. That's at least what we're going to focus on. One is just in the context of a normal argument. The other, though, is to show us that a certain sentence, not an argument, but just a single sentence, is a logical truth. And in a couple of problems here, we'll show you how that works. But let me talk generally now about the strategy of indirect proof. When we use indirect proof, we want ultimately to get to some particular conclusion. Let that conclusion be Q. Now, the idea behind indirect proof is that if you can take the opposite assumption, that is, take not Q, and you can show that from that assumption, through a certain series of steps, you can generate a contradiction. In other words, a statement of the form P and not P, then, since this assumption has led us to a contradiction, that is, a statement which is necessarily false, right? If something which is necessarily false follows from not Q, then we know that not Q itself must be false. Since that's true, that would seem to allow us to infer that Q, its negation, is, in fact, the true statement. This strategy is often referred to by the Latin term reductio ad absurdum. And what this means is that we have taken a certain assumption and shown that it leads to absurdity. When we assume not Q, that leads us to something which is patently absurd, a contradiction. That being true, we know the opposite of the assumption must be the case. Now, just like conditional proof, indirect proof involves a subderivation. We've got something going on inside a subderivation which has begun with this new assumption, and that subderivation has to be discharged out to the outside left-hand line of our derivation. Okay, so there are some similarities between indirect proof and conditional proof, but the big difference is this. In indirect proof, we take the negation of the thing that we are ultimately trying to derive, and in the course of the subproof, we must generate a contradiction. And you should recall from our Unit 12, then, that that's really quite different from conditional proof, which always involves generating a conditional. So let's see if we can take this strategy and apply it to a couple of problems. You're also going to be able to use on Unit 13 conditional proof if in the course of a derivation you feel like that would help you. This first problem gives us probably the most simple application of indirect proof. That occurs when the conclusion that you're hunting for is an atomic sentence. If we want to show W, what we need to do is take the assumption of its negation, not W, and attempt to generate a contradiction inside the subproof. Well, if we had not W, if you look here on line 4, you'll notice that we'll be able to get not K by modus tollens. And if you look at line 1 and 2, we will be able to have both R and also M, the M by modus ponens on line 1 and 2. We can put them together and get K. So here we have a way of getting K and also not K. So we're going to use that contradiction to allow us to generate an indirect proof and discharge the negation of what we assume, and that negation will be this W. So let's start now with our initial assumption. Line 5 will be the negation of what we're hunting for, not W, and that is an assumption of indirect proof. The not W gives us not K, inferred from line 4 and 5 by modus tollens. And now let's get the K. To do that, of course, we have to first do modus ponens on line 1 and 2 and get M. Now we have the R, and remember, just as with conditional proof, information which lies outside the subderivation can be imported, as it were, into the subderivation. That's no problem. So we take advantage of line 1 and line 7 to give us R and M. That's simply conjunction. And now we've got K by modus ponens on line 3 and 8. And notice not K and K. We need to bring them together on one line, so the last line of the subderivation actually says something contradictory, not K and K. And this is lines 6 and lines 9. Conjunction. And really, to make this precisely right, we'll need to simply commute this so we get K and not K, because the indirect proof rule tells us that the line at the end of the subderivation must be of this form, K and tilde K. Alright, so now we have our contradiction in the right order, and that means that we can discharge onto line 12 the negation of our assumption. W is the negation of not W, and so we cite line 5 through 11, indirect proof. Okay, well, let's do one that's slightly more difficult. Here we'll have a conclusion that is not just an atomic sentence, but a disjunction. B or D is our conclusion. Can we use indirect proof to help us on this problem? Well, notice that if we were to take its negation, that would be not B or D. And you'll remember by De Morgan, of course, that's equivalent to not B and not D. And now observe that in line 1, if we had this, we would have the negations of this disjunct and this disjunct, and so by two moves of disjunctive syllogism we would be able to get A and C. Now how's that going to help? Well, if we have the A, of course on line 2 we have not A or C, so by disjunctive syllogism we could get not C, and yet we've already just said that we can get C from line 1. So here's a possible contradiction between C and not C. And in fact, if you were to look at this problem a little bit farther, you'd see that you can get a number of different contradictions from these two premises. We could generate a contradiction on A and not A. We could also generate a contradiction on D and not D. And in fact, could really even generate a contradiction of this whole disjunction. In other words, get B or D, and it's not the case that B or D. Any one of these are possible, and therefore this problem could be solved in a number of different ways. Well, let's go for, let's say, the C and not C version. Remember, we're going to take as our first assumption the negation of what it is we're hunting for, and that is the indirect proof assumption, and by De Morgan that's equivalent to line 4. And now, of course, we have the ability to get into line 1. We need to simplify line 4. In fact, we can do two lines here more or less at once. Both of these are from line 4 by simplification. Now we also need to simplify line 1. And the reason we need to do this, of course, is we're going to use two moves of disjunctive syllogism on the two different parts of line 1. So that gives us C or D on 8 here. That is also line 1, simplification. And now you can see we've got the negation of this and the negation of this. Technically, however, we have to turn these or commute 7 and 8 around in order to apply disjunctive syllogism. So let's get those little moves out of the way. So we have B or A, that's line 7, commutivity, and also D or C, line 8, commutivity. And now we have the negations of these two disjuncts, and so we can infer A, that's from line 5 and line 9, by disjunctive syllogism, and similarly we can infer D, C, that's what we want, and that is from line 8 and line 6, disjunctive syllogism. Okay, now where are we? All of that was a bunch of cleanup steps, really, to get down here to some information that we can use. Well, where we are, of course, if you look at 2 here, is that we have the negation of the first disjunct of 2. That's line 11. That means that we can infer not C from line 2 and line 11 by disjunctive syllogism. And now we've generated a contradiction which simply needs to be placed on a single line, C and not C, and that's simply 12 and 13 by conjunction. There's our contradiction, and so it's time to discharge this entire subderivation, and to do that, recall, you need to place the negation of our initial assumption on the line 15 outside, on the outside left part of the derivation, and so we get our answer, B or D, and we cite everything from 3 through 14 indirect proof. Okay, if we had time, I would go through this problem again and show you that the other contradictions are possible, but really don't worry about what it is you are generating the contradiction from. As long as you can get any contradiction, and of course here's a point that's important to realize, 1/2 of the contradiction can in fact be the very assumption that you take. So if the subderivation begins with not P, for example, if you are able to derive P, that's sufficient. You can then place those two lines together, P and not P, and that constitutes the contradiction. All right, let's do another problem here. This one will be an application of the strategy of indirect proof to a single statement, and our goal here is to show that that statement is a tautology. Now we need to talk a bit about tautologies. You recall that a tautology, or a logical truth, is a statement which is necessarily true. It cannot be false. It guarantees its truth because of its form. Well, one way of thinking about a tautology is that it is as if it were a conclusion from an argument with no premises. In other words, it should be derivable without having to make any additional assumptions. Now that may sound curious to begin with. How can you derive anything when you don't have any premises to begin with? But if you reflect upon it, both the strategy of conditional proof and indirect proof give you the power to do this because of the fact that a subderivation is involved in both of those strategies. If you begin a proof with a assumption for a subderivation, that can be discharged, and you would end up then with a proof whose last line sat on the left by itself with no assumptions above it. When we do this, we've shown that the sentence that we conclude with is in fact a tautology. So let's see how this goes. First, notice that this sentence is a conditional, and so we actually have to make a choice whether to use indirect proof or whether to use conditional proof. Let's be bold and do it both ways. So we'll work this out in two alternative ways to show you how this will go. With conditional proof, actually if you look at this sentence here, you will see that this has to be logically true. Just think of De Morgan here on the antecedent part. That by De Morgan, this would be equivalent to not A or not B, which is just what the consequence says. And obviously, if something is true, then it's true. So we know that this is going to be relatively easy to show. Let's do the conditional proof first. we will then take not A and B as our line 1, and that will be an assumption conditional proof. Line 2 here will be not A or not B, and that's from line 1 and De Morgan. That's, of course, what we were trying to prove, so this is very short this way. We can then discharge the third line, which says not A and B, hooks not A or not B, citing 1 and 2 conditional proof. So it turns out that the conditional proof strategy applied to this tautology gives you a very simple proof. But now, just to illuminate how indirect proof will work on these tautologies, let's work out number 3 alternatively by taking an indirect proof assumption. That, of course, will be the negation of this, and so we need, it's not the case that not A and B hooks not A or not B. And again, we want to say here assumption, but in this case indirect proof. Now, this is very unclear. In order to see what we really have here, we're going to have to manipulate line 1 pretty severely. My suggestion would be that since ultimately we're going to drive this tilde in through the parentheses, if we were to first change the inside sentence from its conditional form to a disjunction, then by driving the tilde in, we will end up with a conjunction on the inside. And that's going to make it more likely we're going to be able to see a contradiction of the form P and not P. So let's do that. So we keep the tilde on the outside first, and we begin by using the implication rule on the inside sentence on line 1, and that, of course, will give us A and B, or not A or not B. And we cite line 1, implication. Now what can we do? We can drive this tilde in through the brackets. We need another bracket here. Drive this in through the brackets, and we get not A and B, and not A or not B. And that's simply line 2, De Morgan. Now, notice that when we take this tilde and use De Morgan on this conjunct, we are going to get the negation of what we have here on the right-hand side. So that alone is sufficient to show that we can generate a contradiction. Let's do the De Morgan step here. That will give us not A or not B, in parentheses, and that is conjoined to its negation. It's not the case that not A or not B. Notice that this is a relatively complex contradiction. It's not a contradiction involving an atomic sentence and its negation, but this is perfectly fine as an instance of a contradiction, and so we're basically done now. We just need to clean up a little bit. This move, again, was line 3, De Morgan. There's our contradiction, and so we discharge an indirect proof, come out with line 5, and we get not A and B, hooks not A or not B, because this is the negation of our initial assumption. And so we cite 1 through 4 indirect proof. So notice here 2 different versions of this problem, one a bit shorter than the other. And I think you'd agree that it's a little bit harder to do with the indirect proof. But that's only a function of this particular problem. In other cases, the indirect proof strategy would actually be preferable. All right, now one last problem. This is the last problem of our entire series. So let's see if we can do this one with a flourish. We want to translate an English sentence, an English argument, into symbolic form first, and then make use of any of the rules, including conditional proof or indirect proof. Here's our argument. If Harry eats 2 cheese blintzes a day, he is not controlling himself. However, if Harry does not blow up like a blimp, then he is controlling himself and is staying slim. It follows that if Harry eats 2 cheese blintzes a day, he will blow up like a blimp. Well, notice that this problem is rather hard to intuitively judge in regard to its validity. So this is one of the powers of having a system of symbolization and deduction. We can, in fact, show whether or not the conclusion follows by relying upon the rules of natural deduction. So we need to first identify our conclusion. It follows that, shows us that this is the conclusion, and it is itself a conditional. Harry eats 2 cheese blintzes a day. We'll let that be H. And Harry will blow up like a blimp. We'll let that be B. So we know that our conclusion here is going to be if H, then B. Our first premise is also conditional. If Harry eats 2 cheese blintzes a day, remember that is H, he is not controlling himself. So we need to symbolize the negation here, the not. He is not controlling himself, then we could symbolize as not C. So our first premise would be if H, then not C. However, if Harry does not blow up like a blimp, then he's controlling himself and is staying slim. We have a conditional here that has a conjunct as its consequent. The first part, or the antecedent of the conditional, is Harry does not blow up like a blimp. That negates our B down here, and so we start out not B. Harry does not blow up like a blimp. Then what? Then he is controlling himself, and so that is C. He's controlling himself, and he's also staying slim. So we need to introduce S here for Harry stays slim, and we need to conjoin that to the C. There's our second premise. Now, what shall we do? Notice that we've got a conclusion which is a conditional proof, so we may well decide that that's the most plausible strategy, conditional proof. Let's think that through a minute. If we assume H, as we would have to do for conditional proof, we would then get not C from line 1 by modus ponens. We would then be looking for B. We could get B, or in effect not B, out of line 2 here by modus tollens if we had the negation of line 2's consequent. So if we had not C and S, we could use modus tollens on line 2 to get our B. And of course, not C and S is equivalent to not C or not S. And we've already said that it is possible for us to get not C. Therefore, it looks like conditional proof as a strategy will very quickly allow us to get the goal sentence B to end the subderivation. And so it looks like we should go with this idea. Assuming H will allow us to derive not C on line 1 by modus ponens. And then now we need to construct the negation of the consequent of line 2. We can do that, of course, by adding not S to 4. And we add not S because then when we do our De Morgan step, the tilde comes outside of the parentheses. This changes to the conjunction, and that's what we need. That negates the consequent of 2. And so we cite line 5 here in De Morgan. And of course it will immediately follow then by modus tollens, not B, on line 2 and 6. And that is the same as B by double negation. And now we have ourselves a conditional proof that has begun with the assumption H, has gone down to conclude B. Therefore, we're allowed to discharge this point and get the answer that we want. H hooks B. And this will be justified by 3 through 8 conditional proof. Okay, congratulations. When you take Unit 13 here in the next day or two, you'll be done. And I hope that these videos have helped a bit and allowed you to get your A. We'll see you maybe in a more advanced logic class sometime.